Those of us who have taken the top of a Coca-Cola bottle or open bottle of champagne are aware of acoustic cavitation. As you take the top off, you release the pressure and you allow the bubbles to come out of solution. Most of us are also aware of how much energy is associated with those bubbles coming out of solution. If you take the cork out of a champagne bottle, it will go for miles, and you can see that there's a lot of energy associated. Similarly, if you look at an old ship's propeller, as the propeller has gone round, cavitation has been produced in the seawater, and that has eaten away the metal of many of these old propellers, as you can see in this picture of an old ship's propeller. Similarly, in tissue, you can produce holes in tissue where you get acoustic cavitation. The bubble activity has caused mechanical damage to that tissue slice. The probability of getting this bubble activity increases the lower the frequency you have, the longer you expose for, and the higher the negative going part of the ultrasound pulse is, so with increasing pressure amplitude. A stably cavitating bubble, so one of these bubbles undergoing these breathing oscillations, will set up fluid patterns around it, and these fluid patterns set up shear stresses on the surface in which they sit, which may be a blood vessel wall, and these can have biological effects. So what sort of biological effects might we expect from an ultrasound beam passing through tissue? Well, on the cellular level, we know we get lysis. Where we get inertial cavitation, the cells are completely broken up. We also can affect the cell's ability to divide, so that's the loss of clonogenic ability. We can produce thermal necrosis, we can cause ultrastructural changes, and also we can get functional changes and membrane effects. So let's look at some of these. The reduction in a cell's ability to divide, which is caused mostly by heating, is shown by a clonogenic assay. In this image, we can see a graph which shows the surviving fraction, so on the y-axis. So this is the number of cells surviving a given heat treatment. On the x-axis, we have the length of time that those temperatures are maintained for. If we look at, for example, the level at which 1/100th, 10 to the minus 2, so 1/100th of the cells that were treated survive, if we look across here, we see that if we treat them at 45 degrees centigrade, it takes 35 minutes before only 1/100th of those cells are surviving, so 99% of them are killed. Whereas if we go to 48 degrees centigrade, the same level of survival is achieved only in about 5 minutes. So you can see the relationship between temperature and time. If we want to cause thermal necrosis, so this is the much higher temperature, the use of much higher temperatures to cause instantaneous cell death, we can also do that, but we usually use a focused beam. Many of us will have used a magnifying glass in the sun to try and set fire to things when we were children. So you can see this in schematic here. Here we have a magnifying glass, which is focusing the sun's rays. In this case, I've shown a pile of logs, but probably as a child it was a pile of dry leaves or a piece of paper. What you will remember is that when you had a big circle of light, so you weren't exactly at the focus of that magnifying glass, then you couldn't set light to whatever it was you were trying to destroy. However, if you put the focus actually on your fuel, on your dry leaf, on your pile of logs shown schematically here, then you can get fire. And we can do something similar with focused ultrasound, where instead of a pile of dry leaves, we have a target we want to destroy. So this is the schematic which shows the principle of high-intensity focused ultrasound, or HIFU. We have an ultrasound source, which in this case is a focusing source. It's a focus bowl in this diagram. You can see that the energy is brought to a focus at a distance from that source, and we can go through the skin and overlying tissue and set our focus only in the target region that we want to destroy. If we do that, and if we put sufficient energy into that beam, then we can we can just destroy the cells in the target volume. Here you can see a piece of porcine liver that we got from the abattoir. You can see that the sound energy goes through the capsule of the liver, and just at in the focal region we have dead cells. These cells have been cooked by the high temperatures that we've reached. If we now look under histology at the margin where essentially where the tissue goes from white to dark red, you can see that there's a very sharp line of demarcation between live cells on the right and dead cells on the left. If we stain for heat shock protein HSP70, which shows us the thermal damage, you can see there's a very specific staining just at the margin of that lesion. If we look at that schematically, you can see that at the edge of this lesion, we have reached a temperature of 55 degrees and held it for a second. In the middle, we will have reached much higher temperatures because we have a Gaussian distribution of temperature across that lesion. We're getting mainly heating, but we may get some acoustic cavitation because we're using very high intensities here. If we look at histologically across this lesion, well, you see a typical island and moat appearance, where right in the middle you get complete tissue destruction. This may be due to boiling bubbles, or it may be due to acoustic cavitation. And as you go out towards the edge of the lesion, you get less and less damage until you get to that very sharp demarcation, the boundary region, as you can see here in our H&E stain. And again, here you see the HSP70 staining that I showed you in the previous slide. We also get ultrastructural damage. This is a piece of mouse uterine tissue that was exposed at much lower intensities, but you can see here a mitochondrion that has been damaged by the ultrasound beam. There are several here mitochondria that are damaged. We also see occasional vacuoles, which may or may not be due to acoustic cavitation. It's hard to tell when you start to do this electron microscopy to know exactly what the exposure was in this section. We know that we get changes in cell membrane permeability, and this may be useful when we want to combine ultrasound for therapeutic uses with chemotherapy. The aim here would be to improve the local delivery and release of a cytotoxic agent, maybe reduce its dose, and therefore to reduce side effects and to increase its efficacy. There are a number of limitations to chemotherapy as it's used at the moment. Systemic administration can lead to normal tissue toxicity. That's obviously a bad thing. Getting drug into tumor cells can be difficult, especially in hypoxic regions where you have poor blood supply. And getting this drug across the extracellular membrane or the nuclear membrane can be problematic for some drugs. So maybe ultrasound can help here. We know that ultrasound can enhance drug delivery. It can have a direct effect on the cells. Ultrasound can have a direct effect on the cells to allow more drug uptake and better cell killing. And this is particularly useful when you want to introduce the drug systemically and use your ultrasound locally to improve drug delivery. You can see here some work. These are clonogenic assays, so these are cells that have been exposed to drug and ultrasound in vitro. On the left, you can see the clonogenic assays. You can see the surviving fraction as a function of drug. On the top, you have adriamycin. On the bottom, we have dornamycin. On the right, you can see the survival curve showing the effect, the fact that we're using levels of ultrasound that in themselves do not kill cells. So if we look again at the left, the curve with the black symbols, the solid black symbols, is the effect of given doses of adriamycin on cell killing. So this is adriamycin alone. And the curve with the open symbols is when you expose the cells to both adriamycin and ultrasound in vitro. And you can see that for any given drug dose, you get more cell killing if you have your ultrasound as well as your drug. So the top curve is for adriamycin, the bottom curve is for dornomycin. So this is for single cells in suspension. We've also done working with 3D models of tumours, so these are cell spheroids. They're often used as a model for a tumour because they do develop hypoxic centres. So here you can see the relative volume of these cells, so relative to the volume on the first day at which you treat them. You see your control cells go on growing. The solid dots show you the growth curves for spheroids that are subjected just to the drug, and the open symbols are for spheroids that are exposed to ultrasound and drug at the same time, and you can see that we have a growth delay for those spheroids. This leads us to the effect known as sonoporation, which is the localized disruption of the plasma membrane, which will allow the diffusion of ions and drugs across the cell membrane. There are a number of hypotheses as to how this works. It may be that we get pore formation or endocytosis, or we just simply open the cell junctions. Pore formation, perhaps that's due to stable cavitation, to inertial cavitation, or to jetting that results from cavitation. Endocytosis is stimulated by the increase in intracellular calcium from pore formation and by the streaming and bubble oscillation stimulation of the mechanosensitive ion channels on the extracellular membranes. This is all hypothesis and still needs to be verified properly. We may be able to open the cell-to-cell junctions by using bubble oscillation or the shear stresses that are occurred by the microstreaming of those bubbles as they vibrate on the membrane. And we get changes in cell layer permeability, certainly to calcium. Maybe there were cytoskeleton changes. A lot of this is still to be shown and to be proven, but this is the hypothesis.